Hi, and welcome to In Search of Truth, where we explore the fascinating stories of history's most transformative events. And I'm your host. Today, we're going to dive into one of the most pivotal moments in human history, the Industrial Revolution. Subscribe to our channel, In Search of Truth, for engaging, informative content that sheds light on the Industrial Revolution's lasting impact.
It attracts any two objects with mass. The more massive an object, the stronger its gravitational pull. Gravity is what holds us to the Earth. It's why objects fall to the ground. Gravity plays a crucial role in the universe. It governs the motion of planets, stars, and galaxies. Without gravity, the universe as we know it would not exist. It is responsible for the formation of stars and planets. Gravity is a universal force. It affects everything in the universe, from the smallest particles to the largest structures. Its influence extends across vast distances, shaping the cosmos. Sir Isaac Newton, one of the most influential scientists in history, developed the groundbreaking law of universal gravitation in the late 17th century. This fundamental law states that every object in the universe, no matter how big or small, attracts every other object with a force that we call gravity. The strength of this gravitational attraction depends on two crucial factors that Newton identified through his meticulous observations and calculations. The first factor is the mass of the objects involved. More massive objects, such as planets and stars, exert a stronger gravitational pull compared to smaller objects like pebbles or dust particles. The second factor is the distance between the objects. As the distance between two objects increases, the gravitational force between them weakens exponentially. Newton's formulation of the law of gravitation was a monumental breakthrough that revolutionized our understanding of the cosmos and the forces that govern it. This law provided a clear explanation for why planets orbit the sun in elliptical paths rather than in perfect circles, as previously thought. It also enabled scientists to calculate the precise gravitational force between any two objects, paving the way for more accurate predictions and models of celestial movements. Newton's work laid the foundation for the field of classical mechanics, which describes the motion of objects under the influence of forces, and significantly advanced the study of astronomy. Even today, centuries later, Newton's law of gravitation remains a fundamental principle in physics, guiding modern scientific research and space exploration. Gravity is responsible for the formation of stars and planets. Clouds of gas and dust in space are drawn together by their own gravity. As they collapse, they heat up and eventually ignite, forming stars. Planets form from the leftover material orbiting a young star. Gravity pulls these particles together, gradually accumulating into larger and larger bodies. Over millions of years, this process can create entire solar systems. Gravity plays a crucial role in the evolution of galaxies. It holds galaxies together in clusters and shapes their spiral structures. We experience gravity constantly, even if we don't always realize it. When we jump, gravity pulls us back down to the ground. When we throw a ball, gravity causes it to follow a curved path. The tides are another example of gravity's influence. The gravitational pull of the moon and the sun causes the water in Earth's oceans to bulge, creating high and low tides. Gravity is essential for life on Earth. It holds our atmosphere in place, providing the air we breathe. Section 5. A cosmic ballet. Gravity's role in celestial motion. Gravity is the choreographer of the cosmos. It dictates the orbits of planets around stars, moons around planets, and stars within galaxies. The intricate dance of celestial bodies is a testament to gravity's invisible hand. The speed and shape of an object's orbit depend on the mass of the object it's orbiting and the distance between them. For example, planets closer to the sun orbit faster than those farther away. Gravity can also cause objects to collide. For example, asteroids can be pulled out of their orbits by the gravity of planets, potentially leading to impacts. Section 6. Beyond Newton, Einstein's revolutionary theory of general relativity. In the early 20th century, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. Einstein proposed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric, and if you roll a marble across the trampoline, it will curve inward towards the bowling ball. Similarly, massive objects warp the fabric of space-time, causing other objects to move towards them. Section 7. Warping space and time. Gravity's influence on the fabric of the cosmos. Einstein's theory of general relativity has some profound implications. It predicts that time slows down in stronger gravitational fields. This phenomenon, known as time dilation, has been experimentally verified. General relativity also predicts the bending of light around massive objects. This effect, called gravitational lensing, can be observed when light from distant galaxies is distorted by the gravity of intervening galaxy clusters. These predictions demonstrate that gravity is not simply a force but an intrinsic property of the fabric of the universe itself. Section 8. Black holes. Gravity's ultimate triumph. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse at the end of their lives. The gravitational pull of a black hole is so intense that it creates a singularity, a point of infinite density at its center. The event horizon marks the boundary beyond which escape from the black hole's gravity is impossible. Black holes are some of the most enigmatic objects in the universe, and they continue to fascinate scientists today. Section 9. Gravitational waves, ripples in space-time. Einstein's theory of general relativity also predicted the existence of gravitational waves. These are ripples in the fabric of space-time caused by the acceleration of massive objects. Gravitational waves travel at the speed of light, carrying energy away from the objects that created them. They are incredibly weak and difficult to detect. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first direct detection of gravitational waves. This discovery confirmed Einstein's prediction and opened a new window into the universe. Section 10. Unraveling the mysteries, the quest to understand gravity's quantum nature. While general relativity describes gravity on large scales, such as the motion of planets and the bending of light around massive objects, physicists are still working to unify it with quantum mechanics, the theory that governs the behavior of matter and energy at the atomic and subatomic levels. Quantum mechanics has been incredibly successful in explaining the interactions of particles and forces at the smallest scales, but it doesn't incorporate gravity. One of the biggest challenges in modern physics is to develop a theory of quantum gravity that can explain gravity's behavior at the smallest scales, where the effects of both quantum mechanics and general relativity are significant. Such a theory would have profound implications for our understanding of the universe's origins and evolution, potentially shedding light on the moments just after the Big Bang and the nature of black holes. String theory and loop quantum gravity are two promising approaches to quantum gravity. String theory suggests that particles are one-dimensional strings, while loop quantum gravity proposes that space-time itself has a discrete structure. Despite significant progress, a complete and consistent theory remains elusive. The quest to understand gravity's quantum nature continues to be one of the most exciting and challenging frontiers in modern physics. Section 11. Conclusion: Gravity's enduring influence. Gravity is a fundamental force that shapes the universe at all scales. It is the invisible hand that governs the motion of celestial bodies and dictates the structure of the cosmos. From the fall of an apple to the motion of galaxies, its influence is ubiquitous. This force, though seemingly simple, is responsible for the complex dance of planets, stars, and galaxies. Newton's law of universal gravitation provides a classical description of gravity, explaining how every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. While Newton's equations were groundbreaking, Einstein's theory of general relativity offers a more profound understanding of its nature as a curvature of space-time. This theory revolutionized our perception of gravity, showing it not as a force, but as a warping of the fabric of space and time. The study of gravity continues to push the boundaries of human knowledge. Researchers and scientists around the world are constantly exploring new ways to understand and measure this force. The detection of gravitational waves, ripples in space-time caused by violent cosmic events, and the ongoing search for a theory of quantum gravity promise to reveal even more about this fundamental force and its role in the cosmos. These discoveries open new windows into the universe, allowing us to observe phenomena that were previously beyond our reach. Understanding gravity is crucial for unraveling the mysteries of the universe. It is the key to unlocking the secrets of star formation, galaxy evolution, and the behavior of exotic objects like black holes and neutron stars. It allows us to study the evolution of stars and galaxies, tracing their life cycles from birth to death and understanding the processes that drive their transformations. Explore the nature of black holes, these enigmatic regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. Black holes challenge our understanding of physics and push the limits of our knowledge, and search for evidence of new physics. The quest for a unified theory that reconciles general relativity with quantum mechanics is one of the most profound challenges in modern science. As we delve deeper into the nature of gravity, we gain a greater appreciation for the intricate workings of our universe. Each discovery brings us closer to understanding the fundamental laws that govern everything from the smallest particles to the largest cosmic structures, revealing the beauty and complexity of the cosmos.